So what is a first-order partial derivative of a multivariable function? Well, inspired by our preview activity, we can define a partial derivative of a single variable function as exactly the slope of a tangent line to a vertical trace parallel to one of the coordinate planes of the graph. In other words, what we do to compute a partial derivative is we replace one or more, let's say this, we'll replace all but one of the input variables to my multivariable function with constants, and thereby focus on just a slice, just a single variable trace, which is a curve, a single variable function, which describes just the dependence of that function on a change in that one variable at a time, where the other variables are all being held constant. And then the regular single variable concept of a derivative then becomes what we call the concept of a partial derivative in the context of a multivariable function. So in this example from the text, we take this function of x and y, which is, it purports to tell us how far is a projectile going to go if I have an angle of y as my launch angle, measured relative to the ground, and my initial velocity is x feet per second, right? So it depends on those two things. If I launch it with a higher initial velocity, then probably the range is going to be longer, right? It's going to go farther. And the dependence on the angle has the sinusoidal quality to it, right? That if I launch at an angle of 0, I'm not going to get any range. If I launch at an angle of 90 degrees, my ball is going to go straight up and come straight down, and so I get no range at all. And in between, it kind of goes up and then goes down. And so if I want to know what is the rate of change of this function with respect to just changes in the x direction, so if I only change my launch velocity and I keep my angle fixed, then how does the range of my projectile end up changing? And so the idea here is that they evaluate, they plug in a constant value for y, get a single variable function, and then compute the derivative with respect to the only variable that's left, the x variable, of that single variable function. And we can do the same thing to study the y partial derivative. Right? Evaluate the function with a constant value of x, and so y becomes my only variable, and then take the derivative of that function with respect to y to get a derivative in the y direction. And again, as I was saying in the first activity, what we're really doing is we're taking a trace. A trace at a constant value of y gives me a trace in the x-axis direction. And then a slope of a tangent line to that curve is also going to give me the slope of a line that's tangent to my graph in three-dimensional space. And that line is going to be somehow parallel to the xz plane here, because only x is varying and y is being held constant. So it's the rate of change of z with respect to x, if you like. And if I do it the other way, if I take a slice at a constant value of x, then that slice is going to be parallel to the yz plane, because x is not changing and only y and z are allowed to change. And the slope of a tangent line to that curve is the same as the slope of some sort of tangent line drawn to this graph in 3 dimensions that's parallel to the xz plane, because parallel to the yz plane, because x is being held constant. So what does this tell us that we can do? Well, it tells me that I can define a derivative, a notion of derivative for a multivariable function, by treating all but one of its input variables as constants, and only letting that variable that I'm interested in vary. So if I want to define what's called the partial derivative in the x-coordinate direction of a function of x and y, I'm going to find the limit of the slopes of secant lines where my secant lines are taken at 2 different x values, separated by an amount h, but they're taken at the same y value. So my y value is being held constant, and it's my x value that has 2 different values in the numerator of this difference quotient. And then I let that difference shrink to 0 in the limit. And so I get the ordinary notion from single variable calculus of a derivative. It's just that my y variable is being treated like a constant, and my x variable is being treated like a variable when I compute the x-coordinate partial derivative. Conversely, if I compute the y-coordinate partial derivative, I'm going to treat the x variable as though it's a constant, and I'm going to let the y variable act like a variable. So let's turn the next activity over to your teams, and I've cut it up into a few different parts because I kind of want us to have some frequent check-ins with this one. So we start with this multivariable function, xy squared over x plus 1, and your job is going to be to, first of all, come up with a formula that describes its trace in the plane y equals 2, and then find its partial derivative. Then come up with a trace in the plane x equals 1, and find a slope of its tangent line, and so find its y partial derivative, and then relate those to the two sketches that you made here. And I've included these sketches already in your write-ups, so you don't have to worry about making these sketches of the traces themselves. So here is the trace in the vertical plane y equals 2, with the point in question at 1, 2 labeled, the point where we're interested in the partial derivatives. And then I've also put in here the trace of the function in the vertical plane x equals 1 and labeled the point where y is equal to 2. So again, the point that corresponds to 1, 2 on our graph. So let's take 5 or so minutes for you to do, let's do parts A and B just to get started with your teams in this initial activity. So first of all, you took this function and set the value of y equal to a constant and only let x vary. And in doing that, you reduce this multivariable question into a single variable question about the function f of x comma 2, 4x over x plus 1. That's the function whose graph as a function of one variable looks like this. And so when you find the derivative of this single variable function at x equals 1, what you're really computing is the partial derivative of the multivariable function at the point 1, 2. So it's like we set y equal to a constant, then we take the x derivative and set that equal to x equals 1 to find the slope of a tangent line to this curve in 2 dimensions, to this trace. Right? And that slope being 1 comports with the sort of 45-degree diagonal line that looks like it would be tangent to this curve at that point. Right? So far so good. One of the things I just did want to mention real quick too, and I made this comment to both of your groups as you were working, is that what we should be careful in how we use notation for derivatives. And for the most part, we're going to avoid using primes to denote derivatives unless we have a function where it's really obvious that there's only a single variable in it. I'm going to prefer the Leibniz notation to just remove that ambiguity. In single variable calculus, we got away with using the prime notation, which was Newton's notation for derivative, because there was only a single input variable, and so it was not ambiguous. Whereas if I have a multivariable function, I can't use prime anymore because that prime doesn't tell me which of my variables I'm taking a derivative with respect to. So that's why the authors of our book prefer this subscript notation. So we can think of the subscript x as being like a prime, right? It's telling us we're taking a derivative, and that derivative is being taken in the x direction. There is an alternative Leibniz version of this notation that we could use also. I don't know if our textbook authors mention it, but because it's pretty common in a lot of places, let me just add that in there as well. For the Leibniz notation, what we would use is something that looks like the partial derivative of f with respect to x, df by dx, evaluated at 1, 2. So I would do here subscript 1, 2 or something like that. Except we do something just a little bit different. Oh boy, this is getting me all mixed up here. We do things a little bit different for partial derivatives than for ordinary derivatives, and instead of using this regular English letter d to represent a partial derivative, we make a curly d. So it's a curly d for a partial derivative. There are both kind of historical and also mathematical reasons for that choice. But if you see that notation being used elsewhere, I don't think our authors use it very much, but it means the same thing. It's the sort of the analog in the Leibniz notation of the subscript variable, which is more like the Newton notation for a derivative, just in sort of using partial derivatives instead of ordinary. And so because that partial derivative is 1, that comports with the slope of the tangent line to this trace of my graph being equal to 1. Okay. Same story for parts C and D, and it looks like this group has already done it. If you haven't, let's just take another 2 or 3 minutes to do parts C and D to this, and then we're going to move forward after this to sort of figure out what should our mental shortcut be to compute partial derivatives without having to plug in constants for our variables.